Somewhere in the southern sky, hidden next to a brighter star, sits the nearest sun to our own. It's barely visible, almost forgettable, and yet reaching it would push human technology and human patience to its absolute limit. So here's the question that's haunted astronomers for decades. If we sent Voyager 1 to Proxima Centauri right now, would it even arrive before humanity itself is gone? If you love the mysteries of deep space as much as I do, please subscribe to the channel. Now let's get started. On September 5, 1977, a Titan Centaur rocket thundered off the launch pad at Cape Canaveral in Florida. Aboard it was a spacecraft roughly the size of a compact car, about 825 kilograms, with a large dish antenna, a collection of scientific instruments, and something that might be the most poetic object humanity has ever created. A golden record, yes, a literal golden record, 12 inches of gold-plated copper etched with sounds and images from our world. It held music from Bach and Beethoven, Chuck Berry, and traditional songs from cultures across the globe. It carried greetings in 55 different languages, the sound of a mother's first words to her newborn child, the call of a humpback whale echoing through the deep ocean, laughter, thunder, the sound of wind through tall grass. Humanity had, in the most literal sense, packed a message in a bottle and thrown it into the cosmic sea, just in case someone, or something, was out there to find it. But here's what you need to understand. Interstellar travel wasn't the original plan. Voyager 1 was built for a much closer mission. Its primary objective was to study Jupiter and Saturn, two of the most spectacular worlds in our solar system, and it delivered far beyond anyone's expectations. When Voyager 1 swung past Jupiter in March of 1979, it captured images that left scientists stunned. The Great Red Spot, a storm larger than Earth itself, was revealed in vivid, swirling detail. The Moon Io turned out to be the most volcanically active body in the entire solar system, with plumes of sulfur erupting hundreds of kilometers above its surface. Europa showed signs of a cracked, icy shell hinting at a liquid ocean hidden below. These weren't just photographs, they were revelations. Then came Saturn. In November of 1980, Voyager 1 gave us our closest look yet at the ringed giant. The rings turned out to be far more complex than anyone had imagined. Thousands of individual bands, braided and twisted by the gravitational tug of nearby moons. The moon Titan was shrouded in a thick, orange atmosphere, tantalizing scientists with the possibility of chemistry that might resemble early Earth. Every image, every data point was a gift, a postcard from the outer solar system delivered by a machine built by human hands. But then something extraordinary happened. After completing its primary mission, Voyager 1 didn't stop. It couldn't stop. There was nothing to stop it. With no friction in the vacuum of space, it simply kept going. The gravitational assists it had received from Jupiter and Saturn had flung it onto a trajectory that angled upward out of the plane of the solar system and into the unknown. It was never going to come back. Decade after decade, Voyager 1 kept traveling. The 1980s passed, the 90s, the 2000s. Each year, it pushed a little farther from the warmth of our sun into the cold and silent outer reaches of the solar system, past the orbits of Uranus and Neptune, past the Kuiper Belt, past structures and regions that had never been visited by anything from Earth. Then, in 2012, 35 years after launch, scientists confirmed something historic. Voyager 1 had crossed the heliopause. That is the boundary where the sun's solar wind, the constant stream of charged particles blowing outward from our star, is finally overwhelmed by the pressure of interstellar space. The spacecraft had left the sun's direct influence. It had entered interstellar space, the vast cold gap between the stars. It was the first human-made object to ever do so. Pause on that for a second. In the entire 4.5 billion year history of our solar system, in the hundreds of thousands of years of human existence, In all of recorded history, not once had anything from Earth crossed that boundary. Not until 1977, when a team of engineers and scientists at NASA's Jet Propulsion Laboratory built a spacecraft, launched it on a column of fire, and sent it sailing into the interstellar medium. That moment in 2012 wasn't just a mission milestone, it was one of the most significant events in the history of our species. Quiet, almost invisible to most of the world, but monumental. By the time you're watching this video, Voyager 1 is somewhere around 23 to 24 billion kilometers from Earth. That number is so enormous it doesn't register the way it should. So let's make it real. Light travels at approximately 300,000 kilometers every single second. At that speed, it takes sunlight about 8 minutes and 20 seconds to travel from the Sun to Earth. Light from the Moon reaches you in about 1.3 seconds, and yet a signal from Voyager 1, traveling at the speed of light, takes over 22 hours to reach us, more than an entire day, at the fastest speed physically possible in the universe. That is how far away Voyager 1 is right now, and we built it in 1977, with technology that, by today's standards, is almost laughably primitive. The computer aboard Voyager 1 has less processing power than the watch on your wrist. And yet there it is, still transmitting data, still sailing through the dark, billions of kilometers from home. Now here's where things get genuinely mind-bending and a little humbling, because as far as Voyager 1 has traveled, as incomprehensibly distant as it is from Earth, it has barely left the neighborhood. When you set its position against the distance to even the nearest star, the spacecraft might as well be standing at your front door, staring at the street, because Proxima Centauri isn't 24 billion kilometers away, it's 40 trillion kilometers away. And that gap, that almost incomprehensible gulf between those two numbers, is what this entire video is really about. So let's talk about Proxima Centauri itself, because before we crunch the travel time, you need to feel the distance. Really feel it. Proxima Centauri is a red dwarf star, the most common type of star in the Milky Way galaxy. It's small, dim, and burns cool compared to our Sun. If you placed our Sun and Proxima Centauri side by side, the Sun would look like a brilliant golden lamp and Proxima would look like a dying ember. It emits only about 1/500th of the light our Sun does. It's part of a three-star system known as Alpha Centauri, a system that has captured human imagination for centuries. Alpha Centauri A and Alpha Centauri B are two sun-like stars orbiting each other in a slow, ancient gravitational dance. And then there's Proxima, a small, separate companion orbiting far out on the edges of the system, completing one loop around its two partners roughly every 500,000 years. And at 4.24 light-years from Earth, it is the closest star to us. Of the more than 300 billion stars in the Milky Way, Proxima Centauri is our nearest cosmic neighbor. Our nearest, and it is almost unfathomably far away. 1 light-year, the distance light travels in 1 full year, is approximately 9.46 trillion kilometers. Multiply that by 4.24, and you get roughly 40.1 trillion kilometers between Earth and Proxima Centauri. Let's put that in a different kind of perspective. If you were to drive a car at 100 kilometers per hour, a reasonable highway speed, and you drove non-stop 24 hours a day, 7 days a week, the journey to Proxima Centauri would take you approximately 45 billion years. That is more than 3 times the current age of the universe. Or try this. If you shrank the distance from Earth to the Sun, 150 million kilometers, down to just 1 centimeter, then on that same scale, Proxima Centauri would be sitting about 4.3 kilometers away from you. 4 kilometers on a map where the Earth's entire orbit around the Sun fits on the tip of your finger. That is the void between stars. It isn't just empty space. It is a scale of emptiness that has no real comparison in human experience. No road trip, no ocean crossing, no mountain climb prepares your mind for it. It exists entirely outside the realm of anything our ancestors, or any human being, has ever had to navigate. And yet, here we are, a young species barely a blink old in cosmic terms, already asking, how long would it take to get there? Once you understand how long Voyager 1 would take to reach Proxima Centauri, a natural question follows. Okay, but where does it actually end up over truly vast stretches of time? I made a video covering where Voyager 1 will be in 1 billion years. It's on the card above. And the answer will completely reshape how you think about time and space. The link is pinned on the comments and on the description, but right now, Voyager 1 is traveling at approximately 61,000 kilometers per hour relative to the Sun, 61,000. That sounds extraordinary, and in human terms it absolutely is. Nothing we have ever built and launched has moved faster through space on a sustained basis. No car, no jet, no rocket that has ever carried a human being comes close to that kind of speed. To put it in context, the fastest commercial aircraft ever built, the Concorde, flew at just over 2,100 kilometers per hour. The SR-71 Blackbird, the legendary American reconnaissance aircraft, and one of the fastest air-breathing planes in history, reached a top speed of about 3,500 kilometers per hour. Even the fastest crewed spacecraft ever, the Apollo 10 command module during its return to Earth in 1969, hit a peak of roughly 39,900 kilometers per hour, and Voyager 1 blows past all of those at 61,000 kilometers per hour. Voyager 1 covers about 1.46 million kilometers every single day. In 1 year, it travels roughly 533 million kilometers. That's fast, genuinely fast. It's the kind of speed that makes you feel proud to be human, proud that we built something capable of this, launched it into the void, and watched it go. There's something deeply moving about that, but now let's hold that speed up against the distance to Proxima Centauri, 40.1 trillion kilometers. That's the gap we're trying to cross. Divide 40.1 trillion by 533 million, the number of kilometers Voyager 1 covers in a year, and you get approximately 73,500 years. 73,500 years. Ride that again. Not 73,500 days, not 73,500 months. Years. Full Earth years. Each one 365 days long. Each day 24 hours, each hour 60 minutes. To put that into human history, 73,500 years ago, our ancestors were living through the Upper Paleolithic period. Modern humans had only recently migrated out of Africa. Cave paintings hadn't been made yet. Agriculture wouldn't be invented for another 60,000 years. Writing, the foundation of recorded civilization, was still about 70,000 years in the future. The ancient Egyptians, the Romans, the Greeks, the Renaissance, the Industrial Revolution, the Internet, all of it would still be tens of thousands of years away, and in that time, Voyager 1 would have traveled to the nearest star, one destination, the closest possible target in the entire galaxy. Let that settle in. This is what astronomers mean when they talk about interstellar distances being a fundamentally different category of scale. It's not just that the numbers are big, it's that they exist on a time scale that dwarfs everything humans have ever experienced, built, or imagined. Civilizations rise and fall in centuries. Our entire recorded history spans roughly 5,000 years, and crossing to the nearest star, not exploring it, not orbiting it, not landing, just getting there, would require a journey nearly 15 times longer than all of recorded human history stacked end to end. It's humbling, and it should be, because the universe was not built to accommodate our impatience. Now you might be thinking, okay, but Voyager 1 wasn't aimed at Proxima Centauri. It's heading in a completely different direction. So this whole scenario is hypothetical to begin with. And you're absolutely right. Voyager 1 is currently heading roughly toward the constellation Ophiuchus, angling upward out of the ecliptic plane of the solar system. It is not on any trajectory toward Proxima Centauri, and it never was. Its path was shaped by the gravitational slingshots around Jupiter and Saturn, a brilliant piece of orbital engineering, but one designed for speed and planetary exploration, not interstellar targeting. If we wanted to reach Proxima Centauri specifically, we'd need to launch a spacecraft aimed in the right direction to begin with. And even then, at Voyager's speed, you're looking at that same 73,000-year journey. But here's where it gets really interesting, because scientists and engineers aren't just sitting around accepting that number. Over the past few decades, some genuinely remarkable minds have been asking a different kind of question, not how long at current speeds, but what would it actually take to get there in a human-relevant time frame? And the answers they've come up with range from audacious to almost science-fictional. Let's talk about one of the most exciting real proposals on the table. Breakthrough Starshot, announced in 2016 by the late physicist Stephen Hawking and entrepreneur Yuri Milner. Breakthrough Starshot is a research initiative with a genuinely bold ambition to develop a fleet of tiny, lightweight spacecraft capable of reaching Alpha Centauri within a human lifetime, not in 70,000 years. In roughly 20 years of travel time, the concept works like this. You build an extremely lightweight spacecraft called a Starship, about the size of a postage stamp, weighing just a few grams. You attach a thin reflective sail to it, a light sail, measured in square meters but with a mass of almost nothing. Then, from the ground or from orbit, you fire a powerful laser, an array of lasers actually, with a combined power output of around 100 gigawatts, directly at that sail. The pressure from the laser light pushes the sail. Because the spacecraft is so extraordinarily light, the acceleration is incredible. In theory, the Starship could be accelerated to roughly 20% of the speed of light within just a few minutes of laser firing, 20% of the speed of light. That is approximately 60,000 kilometers per second. Compare that to Voyager 1's 61,000 kilometers per hour. We're talking about a speed that is roughly 3,500 times faster than our fastest current spacecraft. At 20% of light speed, the journey to Proxima Centauri would take approximately 21 years. 21 years, not 73,000. A human lifetime, a career, the gap between a child's birth and the beginning of adulthood. That is the promise of Breakthrough Starshot. And it isn't science fiction, at least not entirely. The physics are real. Laser propulsion is a genuine concept with theoretical underpinnings that hold up under scrutiny. The challenges are enormous. Engineering a light sail that can survive the intense laser bombardment without vaporizing, pointing a 100 gigawatt laser array with the precision needed to keep the sail on target, building onboard electronics small enough to fit on a postage stamp while still being capable of capturing data and transmitting it across 4 light years. But none of these are violations of the laws of physics. They're engineering problems, hard ones. But engineering problems, not impossibilities. Now, 20% of light speed raises its own fascinating complications. At that velocity, relativistic effects start to become relevant. Time dilation, one of the stranger and more beautiful consequences of Einstein's special theory of relativity, means that time passes slightly differently for the spacecraft compared to observers on Earth. The difference at 20% of light speed isn't dramatic, but it's real. And if we ever imagine pushing spacecraft to 50, 60, or even 90% of light speed, relativistic effects become central to the entire mission design. But let's stay grounded for now, because even Breakthrough Starshot, as inspiring as it is, faces obstacles that remain deeply unsolved. The power requirements alone are staggering. 100 gigawatts is roughly the total electrical generating capacity of a small country. Building and pointing that array with the necessary precision is a challenge that would require global cooperation and resources on a scale humanity has never attempted for a scientific project. And then there's the communication problem. Even if a starship reaches Proxima Centauri in 21 years, sending data back would take another 4.24 years at the speed of light. So the earliest we'd receive any information from such a mission is roughly 25 years after launch, and the data that tiny spacecraft could transmit across 4 light years with a transmitter that weighs a fraction of a gram would be extraordinarily limited. These aren't reasons to abandon the dream. They're reasons to keep pushing, to keep engineering, to keep imagining, because every major leap in human exploration has come from people who refused to accept the current state of the art as the final word. Think about it this way. In 1903, the Wright brothers flew a heavier-than-air aircraft for 12 seconds, covering 37 meters. 66 years later, Neil Armstrong stepped onto the surface of the moon. The leap from Kitty Hawk to Tranquility Base happened within a single human lifetime. If you had told someone in 1903 that within their lifetime, humans would walk on another world, they would have looked at you like you were dreaming. We are always dreaming. And then, slowly, stubbornly, we make the dreams real. So where does that leave us with Voyager 1 and Proxima Centauri? Here's the honest, grounded truth. At its current velocity, even if Voyager 1 were headed straight for Proxima Centauri, which it isn't, the spacecraft would arrive in approximately 73,500 years. Long after every human alive today has turned to dust. Long after most of what we consider civilization has either transformed beyond recognition or ceased to exist entirely. And yet, and this is the part that I find genuinely moving, Voyager 1 is out there, right now, sailing through interstellar space. A machine born from human curiosity, still alive, still transmitting, still crossing the void. Its nuclear power source, a radioisotope thermoelectric generator using the decay of plutonium-238, is slowly fading, and scientists estimate that by around 2025, the spacecraft may no longer have enough power to operate any of its scientific instruments. Eventually, the signal will go quiet. The golden record will drift on in silence, but it will keep moving. In the absence of anything to stop it, no friction, no significant gravitational drag at interstellar distances, Voyager 1 will continue its journey essentially forever or until something intercepts it, which, given the emptiness of interstellar space, is unlikely for an extraordinarily long time. There's something profound about that. This object, built by humans, carrying human voices and human music and a human vision of the cosmos, will outlast our civilization, our species, perhaps even our planet. It is, in a very real sense, the most durable artifact our civilization has ever produced, and it's moving at 61,000 kilometers per hour toward the stars. Forever now, we're going to zoom out even further. We're going to talk about what Proxima Centauri is actually like up close, because in 2016, astronomers made a discovery there that changed everything. A discovery that made the question of reaching that star feel less like an abstract thought experiment and far more like an urgent, burning ambition. There's a planet there, and it sits in the habitable zone. In 2016, astronomers made an announcement that sent a quiet tremor through the scientific community and lit up headlines around the world. A team of researchers using the European Southern Observatory's facilities in Chile, specifically the HARP spectrograph at the La Silla Observatory, had detected something extraordinary orbiting Proxima Centauri. A planet, not just any planet, a rocky, Earth-sized world, orbiting its star at a distance that placed it squarely within what scientists call the habitable zone, the region around a star where liquid water could, in theory, exist on a planetary surface, the region where life as we know it might be possible. They called it Proxima Centauri b, and in an instant, the nearest star to our Sun stopped being just an interesting astronomical object and became something far more charged with meaning. It became a destination. Now, and this is important, having a planet in the habitable zone does not mean that planet is habitable. That distinction matters enormously, and any honest conversation about Proxima b has to hold both the excitement and the uncertainty at the same time. Science demands that. And the truth is, the reality of Proxima b is complicated, fascinating, and in many ways deeply sobering. Let's start with what we actually know. Proxima b has a minimum mass of approximately 1.17 times that of Earth. It orbits its star every 11.2 days. A year on Proxima b lasts less than 2 Earth weeks, and it sits about 7 million kilometers from Proxima Centauri, which sounds incredibly close compared to Earth's 150 million kilometer distance from our Sun. But because Proxima Centauri is such a cool, dim star, that tight orbit still puts Proxima b within the temperature range where water could theoretically remain liquid. On paper, that's remarkable. On paper, this is the most Earth-like planet we've ever found in terms of mass and orbital positioning around the nearest star to our own. You can understand why the discovery caused such a stir. But here's where the complications begin, and they are significant. Proxima Centauri is a red dwarf, and red dwarfs, despite being the most common type of star in the galaxy, are in many ways deeply hostile to the kind of life we're familiar with. The same qualities that make them long-lived and abundant also make them, at least potentially, dangerous neighbors. Red dwarfs are magnetically active, violently so, especially when they're young. Proxima Centauri in particular is classified as a flare star, a star that periodically releases intense bursts of ultraviolet radiation and X-rays. These flares can be sudden and dramatic, sometimes increasing the star's brightness by several times within minutes. And for a planet orbiting as close as Proxima b does, those flares aren't a distant inconvenience. They're a direct, repeated bombardment. In 2019, astronomers detected what they described as a superflare from Proxima Centauri, an event roughly 100 times more powerful than the largest solar flares ever recorded from our own Sun. If Proxima b lacks a strong magnetic field and a thick atmosphere to absorb and deflect that radiation, the surface conditions could be extraordinarily harsh for any complex chemistry, let alone biology. Then there's the question of tidal locking. Because Proxima b orbits so close to its star, most planetary scientists believe it is likely tidally locked, meaning the same side of the planet always faces the star, just as the same side of the Moon always faces Earth. One hemisphere would be in perpetual daylight, baked under the dim but constant glow of Proxima Centauri. The other would be frozen in eternal night. The terminator line between them, a permanent ring of twilight circling the planet, might be the only region where temperatures are moderate enough to sustain liquid water. Whether an atmosphere could survive under these conditions, whether it could redistribute heat effectively enough to prevent the night side from freezing solid and the day side from baking dry. These are questions that current technology simply cannot answer with certainty. We have detected Proxima b, but we cannot yet see it, not directly, not in any meaningful detail, and in 2022, a second candidate planet was reported, Proxima Centauri d, with a mass possibly as low as 1/4 of Earth's mass, orbiting even closer to the star. The Proxima system is beginning to look genuinely complex, with multiple worlds potentially sharing space around this faint red ember. But here's the thing about all of this uncertainty, it doesn't diminish the wonder. If anything, it deepens it, because science, isn't a collection of settled answers. It's a living, breathing process of refining our understanding. Every new piece of data about Proxima b is a step forward, even when that step reveals how much we still don't know, and the fact that a potentially rocky, potentially Earth-massed world exists around the closest star to our Sun, regardless of whether it hosts life, regardless of whether its surface is welcoming or brutal, is one of the most statistically significant facts in modern astronomy, because if planets can form around Proxima Centauri, they can form around red dwarfs in general, and red dwarfs make up roughly 73% of all stars in the Milky Way. The implications ripple outward across the galaxy. There could be hundreds of billions of rocky planets orbiting red dwarf stars throughout our galaxy alone. Some fraction of those will be in habitable zones. Some fraction of those might have atmospheres. Some fraction of those might have liquid water. And somewhere in that cascade of fractions and probabilities, the question of whether we are alone in the universe becomes less abstract and more urgent than it has ever been before. Now, let's bring Voyager 1 back into the picture, because knowing that there might be a world of genuine interest at Proxima Centauri changes the emotional weight of the travel time calculation we did earlier. It's one thing to talk about crossing 40 trillion kilometers to reach a dim, unremarkable star. It's something else entirely to talk about crossing that same distance to reach a star with a planet that might have something extraordinary waiting on it. 73,500 years suddenly feels less like a neutral fact and more like a lament. Think about what that means in terms of our current situation. The discovery of Proxima b was made in 2016. Scientists used the radial velocity method to detect it, watching for tiny, rhythmic wobbles in the star's light caused by the gravitational tug of an orbiting planet. It's an indirect method, extraordinarily sensitive, requiring years of careful observation with precision instruments. And it was only possible because Proxima Centauri is so close. If this same planet existed around a star 50 or 100 light-years away, we might never have found it with current technology. The closeness that makes Proxima Centauri the obvious first target for interstellar exploration is also the reason we know anything about its planetary system at all. Distance is the enemy of discovery, and yet, even at 4.24 light-years, the shortest possible interstellar journey, we are completely, utterly out of reach with our current capabilities. This is the central tension of our moment in history. We are living at the precise point in time when we have become sophisticated enough to detect worlds around other stars, to actually identify them, measure their masses, infer their orbital periods, but we remain hopelessly far from being able to visit them. We can see the shore, but we have no boat capable of crossing the ocean. That gap between knowledge and access is one of the defining features of 21st century astronomy, and it drives a particular kind of hunger in the scientific community, a hunger that shows up in proposals like Breakthrough Starshot, in the development of increasingly powerful space telescopes, in the ongoing search for better propulsion concepts. Because once you know there's something worth going to, the urgency of finding a way to get there becomes very real. If you are enjoying this journey, make sure to subscribe to the channel and give this video a like. You'll get content rooted in real science every day, the kind that stretches your thinking and fills you with that rare, electric feeling of awe. Now let's talk about what it would actually look like to observe Proxima b more closely, because this is where the next generation of technology enters the story. The James Webb Space Telescope, launched on December 25, 2021, after decades of development and a famously turbulent production history, represents the most powerful space observatory humanity has ever deployed. With its 6.5-meter gold-coated mirror and its suite of infrared instruments, positioned at the second Lagrange point, roughly 1.5 million kilometers from Earth. Webb has already transformed our understanding of the early universe, distant galaxies, and the atmospheres of exoplanets, but even Webb faces serious limitations when it comes to Proxima b. The planet is so close to its star that separating its faint light from the overwhelming glare of Proxima Centauri is enormously challenging with current technology. Direct imaging of Proxima b, actually photographing the planet itself and analyzing its light to determine atmospheric composition, remains beyond what Webb can reliably achieve. That's where future concepts come in. NASA has been developing ideas for telescopes specifically designed to image Earth-like planets around nearby stars, separating planetary light from stellar glare using technologies like coronagraphs and starshades. A starshade is essentially a precisely shaped screen, deployed tens of thousands of kilometers in front of a telescope, designed to block a star's light so completely that the far dimmer light of an orbiting planet can be detected. The engineering required is breathtaking in its precision. The starshade must be positioned with an accuracy of about a meter at a distance of perhaps 40,000 kilometers. If such a telescope were ever built and aimed at Proxima b, we might be able to detect the signatures of specific molecules in its atmosphere: oxygen, water vapor, carbon dioxide, methane, and the presence of certain combinations of those molecules in certain ratios would be one of the strongest possible indicators that something biological might be happening on that world. We're not there yet, but the roadmap exists. The scientific community knows what needs to be built. The question, as always, is one of will, resources, and time. And time brings us back to Voyager 1. Because amid all this talk of future telescopes and laser-propelled light sails and potentially habitable worlds, Voyager 1 remains the most honest symbol of where we actually stand. It is the farthest thing we have ever sent into space. It has been traveling for nearly 5 decades. It carries the best of what we were in 1977, our curiosity, our creativity, our audacity, our longing to reach beyond. And at 73,000 years from Proxima Centauri, it is a beautiful, aching reminder that the stars do not come easily. There's a line from the astronomer Carl Sagan that feels deeply relevant here. Writing about our place in the cosmos, he said, "The universe is a pretty big place. If it's just us, seems like an awful waste of space." That sentiment, that mixture of humility and hope, is exactly what the story of Proxima b stirs up. Because whether or not that planet has life, whether or not it has an ocean or an atmosphere or a breathable sky, its existence tells us something important. Planetary systems are everywhere, worlds are everywhere. The universe is far more full of places than we once dared to imagine, and we, this small, fragile, endlessly curious species on a pale blue dot, we are the ones asking the questions. We are the ones building the telescopes, launching the spacecraft, scanning the data. In a cosmos that is roughly 13.8 billion years old, in a galaxy containing somewhere between 100 billion and 400 billion stars, we are the ones who looked up at a faint red point of light 4 light-years away and asked, "Is anyone home?" That impulse, that reaching, is one of the most distinctly human things about us, and no matter how vast the distances turn out to be, no matter how many 73,000-year travel times we have to reckon with, that impulse doesn't go away. It just finds new forms, new tools, new dreams. Let's talk about how we actually get there. Not in 73,000 years, not in a time frame that makes the journey purely philosophical, but in a way that a human being, or at least a human civilization, could realistically anticipate, plan for, and perhaps one day witness. Because the question of interstellar propulsion isn't just an engineering puzzle, it's one of the deepest expressions of human ambition that exists. And the ideas people have come up with to solve it range from the surprisingly practical to the genuinely staggering, to understand why propulsion is so hard at interstellar scales, you first need to understand something fundamental about how rockets work, and why the way they work right now is simply not going to cut it for crossing the space between stars. Every rocket ever launched from Earth operates on the same basic principle described by Newton's third law. For every action, there is an equal and opposite reaction. You throw mass out the back of your spacecraft at high speed, and the spacecraft moves forward. The faster you throw the mass, and the more of it you throw, the faster you go. Simple in concept, brutal in practice. The problem is fuel. To accelerate a spacecraft to higher and higher speeds using chemical rockets, you need to carry more and more propellant. But propellant has mass, and to accelerate that extra mass, you need even more propellant, which adds more mass, which requires more propellant. This vicious cycle, known as the Tsiolkovsky rocket equation, formulated by the Russian mathematician Konstantin Tsiolkovsky in the late 1800s, places hard mathematical limits on what chemical propulsion can achieve. The very best chemical rockets, like the ones that powered the Saturn V that took astronauts to the moon, have an exhaust velocity of around 4.4 kilometers per second. To reach even a fraction of a percent of the speed of light using chemical propulsion alone, you would need a spacecraft where the fuel outweighs the payload by a ratio that is simply physically absurd. We're talking about a fuel mass many times greater than everything humanity has ever manufactured combined. Chemical rockets got us to the moon. They got us to Mars with robotic landers. They launched Voyager 1 on its incredible journey. But for interstellar travel, they are fundamentally, mathematically inadequate. The energy simply isn't there. So what is? Let's start with the most immediately realistic concept that goes beyond chemical propulsion, nuclear thermal propulsion. The idea here is straightforward. Instead of burning chemical propellants to produce heat and thrust, you use a nuclear reactor to superheat a propellant, typically hydrogen, to temperatures far beyond what any chemical reaction could achieve, and then expel it through a nozzle to generate thrust. NASA and the Department of Defense have actually been developing nuclear thermal propulsion concepts quite actively in recent years, with programs aimed at eventual crewed missions to Mars. The exhaust velocities achievable with nuclear thermal engines are roughly 2 to 3 times higher than the best chemical rockets. That's a meaningful improvement for missions within our solar system, cutting a Mars transit time significantly, but in the context of reaching Proxima Centauri, it's still nowhere near enough. You'd shave perhaps 20 or 30,000 years off the journey. You'd still be looking at a trip measured in tens of thousands of years. To get truly serious about interstellar travel, you need to think about propulsion concepts that operate on a completely different energy scale. And that brings us to one of the most audacious and genuinely fascinating ideas ever seriously proposed by aerospace engineers: nuclear pulse propulsion. The concept was developed in the late 1950s and early 1960s under a project called Orion, not the current NASA capsule, but a secret and then semi-public program run by physicists including the legendary Freeman Dyson. The idea was almost shockingly straightforward. You build a large spacecraft with a thick metal pusher plate at the rear. You drop small nuclear bombs, one after another, out the back of the spacecraft. Each explosion pushes against the plate and accelerates the ship forward. Repeat this hundreds or thousands of times, and you achieve velocities that no chemical rocket could ever approach. Dyson and his colleagues calculated that a sufficiently large Orion-type spacecraft, using thermonuclear devices rather than simple fission bombs, could potentially reach velocities of around 3 to 5% of the speed of light. At 3% of light speed, a journey to Proxima Centauri would take roughly 140 years. At 5%, around 85 years, still a very long time, still longer than a single human lifetime. But suddenly we're talking about a multi-generational mission, a ship that launches with one crew and arrives with their great-grandchildren. Not a fantasy, a genuinely conceivable, if extraordinarily challenging, undertaking. The Orion project was ultimately killed not by engineering failure, but by the Partial Nuclear Test Ban Treaty of 1963, which prohibited the detonation of nuclear weapons in space. Detonating thousands of nuclear bombs in Earth's atmosphere or even in low orbit would have had catastrophic environmental consequences. The radioactive fallout alone would have been an enormous global health crisis. So the program ended, but the physics never went away. And for many serious thinkers in the field of interstellar studies, nuclear pulse propulsion remains one of the most credible near-term pathways to genuine interstellar capability. A more refined version of the concept, developed in the 1970s by the British Interplanetary Society, was called Project Daedalus. Instead of nuclear bombs, Daedalus proposed using small pellets of deuterium and helium-3, ignited by electron beams to trigger fusion reactions. The exhaust from these microfusion explosions would drive the spacecraft forward. The Daedalus study concluded that a spacecraft of this type could reach approximately 12% of the speed of light, cutting the journey to Proxima Centauri to around 36 years, within a human career. You could launch the mission in your 40s, and the data could start coming back before you retire. Of course, the practical challenges are immense. Helium-3 is extraordinarily rare on Earth. It exists in meaningful quantities on the lunar surface and in the atmospheres of the outer planets, but harvesting it at the scale required for a Daedalus-type mission is far beyond current capability. The fusion ignition system would need to fire repeatedly with extraordinary precision, and the spacecraft itself, as designed in the 1970s study, was enormous, roughly 54,000 tons at launch, dwarfing anything humanity has ever constructed in space. But again, the physics works. No laws of nature are being violated. The barriers are engineering and economics, not fundamental impossibility. And that distinction matters enormously because engineering problems yield to time and ingenuity in a way that violations of physical law simply do not. Now let's talk about the concept that genuinely captures the imagination at the far edge of what serious physics permits. Antimatter propulsion. Antimatter is real. This is not science fiction. Antimatter particles are produced routinely in particle accelerators. Facilities like CERN's Large Hadron Collider near Geneva create antiprotons and positrons as a matter of course. When a particle of matter meets its antimatter counterpart, they annihilate each other completely, converting 100% of their combined mass into pure energy according to Einstein's famous equation: energy equals mass times the speed of light squared. This is the most energy-dense reaction physically possible. Nothing releases more energy per unit mass than matter-antimatter annihilation. Nothing. Not nuclear fission, not nuclear fusion, not any chemical reaction. The energy released by annihilating just 1 gram of antimatter with 1 gram of ordinary matter would be equivalent to roughly the same energy released by the atomic bomb dropped on Hiroshima, approximately 43 trillion joules. If you could harness that energy efficiently for propulsion, directing the annihilation products to produce thrust, the theoretical exhaust velocities are close to the speed of light itself. A spacecraft powered by antimatter could, in principle, reach a significant fraction of light speed. At 50% of light speed, Proxima Centauri would be reachable in about 8.5 years, at 90% around 4.7 years. At very high fractions of light speed, relativistic time dilation would kick in meaningfully. The crew aboard the ship would experience less time passing than observers on Earth, The catch, and it is an enormous one, is production. The entire global output of antimatter from all particle accelerators on Earth amounts to a tiny fraction of a gram per year. The cost of producing just 1 gram of anti-hydrogen using current methods has been estimated at somewhere in the range of $62 trillion US. And an antimatter-propelled starship would need tons of the stuff. The gulf between what antimatter propulsion promises and what our current ability to produce antimatter allows is almost comically vast. We are nowhere near bridging it with existing technology. But the concept exists, the physics is solid, and there are researchers who genuinely believe that over the coming centuries, advances in particle physics and energy production could make antimatter synthesis dramatically more efficient. It's a very long game, but it's not an impossible one. There's another concept worth mentioning, one that sits in a slightly different category because it doesn't require carrying fuel at all. We already touched on it earlier, the laser light sail as proposed by Breakthrough Starshot. But there are broader variations on this theme worth exploring. The general concept of beamed propulsion, where energy is transmitted to the spacecraft from an external source rather than carried on board, fundamentally sidesteps the tyranny of the rocket equation. If you don't have to carry your fuel, the mass constraints that strangle conventional rockets simply don't apply. Beyond lasers, researchers have proposed using microwave beaming, particle beams, and even magnetic sails that interact with the interstellar medium, the thin soup of charged particles that drifts between the stars, to generate drag and allow deceleration at the destination. Because here's a problem that often gets overlooked in interstellar travel discussions. Getting up to speed is only half the challenge. You also need to slow down when you arrive. A spacecraft that flies through the Proxima Centauri system at 20% of light speed isn't visiting, it's just passing through too fast to observe anything useful. Deceleration is, in many ways, the harder part of the problem, and it's one that concepts like magnetic sails or dedicated deceleration burns using onboard fuel try to address, each with their own mass and energy trade-offs. There's also the question of what you send. Not every interstellar mission needs to carry a human crew. In fact, the most credible near-term scenarios almost certainly don't. Sending a human being or many human beings on an interstellar journey introduces an avalanche of additional complexity. Life support, food, water, radiation shielding against the high-energy particles that fill interstellar space, psychological well-being during years or decades of isolation, medical care, the simple fact that human bodies are fragile, maintenance-intensive, and have a limited operational lifespan. Robotic probes, or eventually artificially intelligent systems, don't have these problems. They don't need to eat, they don't suffer from isolation. They can be put into low-power states during the cruise phase and reactivated at the destination, and they can be made much lighter than any crewed spacecraft, which matters enormously for the acceleration calculations. The most realistic vision of a first interstellar mission looks something like Breakthrough Starshot. Tiny, lightweight, automated probes, accelerated to a significant fraction of light speed by an external energy source, flying through the target system, collecting data and beaming it back. No landing, no extended exploration, just a flyby, a first breathless glimpse. But even a flyby of Proxima b, even a few hours of data collected as a tiny spacecraft hurtles through the system, would be among the most significant scientific events in human history. If those instruments detected anything suggesting atmospheric chemistry, surface liquid, or, dare we imagine it, signs of biological activity, the world would never be the same again. We stand at the very beginning of this story. The chapters ahead are long and uncertain, but the first lines have already been written by the engineers who built Voyager 1, by the astronomers who found Proxima b, by the physicists who filled whiteboards with equations about light sails and antimatter and fusion drives. Every one of them is part of the same long, luminous tradition of human beings who looked up at the stars and refused to accept that they were simply out of reach. Let's talk about time itself, because once you start dealing with speeds anywhere close to the speed of light, time stops behaving the way your intuition expects it to. Albert Einstein's theory of special relativity, published in 1905, tells us something strange and beautiful. Time is not a fixed universal river flowing at the same rate for everyone. It's flexible. It bends depending on how fast you're moving. The faster you travel relative to someone else, the slower time passes for you compared to them. This isn't speculation. It isn't a fringe idea. It's been tested, verified, and confirmed thousands of times. Atomic clocks flown on airplanes tick at very slightly different rates than identical clocks left on the ground. GPS satellites orbiting Earth have to correct for time dilation every single day, or the entire global positioning system would drift wildly inaccurate within hours. Relativity isn't a theory in the casual sense of the word. It's one of the most rigorously confirmed frameworks in the history of science. Now imagine applying that to an interstellar journey. If you built a spacecraft capable of reaching, say, 80% of the speed of light, a staggering achievement by any measure, the crew on board wouldn't experience time the same way people back on Earth would. For every year that passes on that ship, roughly 1.67 years would pass back home. Push the speed up to 99% of light speed, and the ratio becomes even more dramatic. For every year the crew experiences, about 7 years would pass on Earth. At those speeds, a journey to Proxima Centauri that takes just a few years from the crew's perspective could correspond to many more years passing for everyone they left behind. The astronauts would step off their ship having barely aged, only to find that friends, family, maybe even entire generations back on Earth had lived and died in their absence. There's something almost tragic about that, and something wondrous too, because it means that, in principle, given enough propulsive power, a human being could travel distances that would otherwise take lifetimes while experiencing only a fraction of that time personally. Relativity, in a strange way, makes the universe a little smaller for the traveler, even as it remains just as vast for everyone who stays behind. Of course, we are nowhere near building anything that could approach even a modest fraction of light speed with a human crew aboard. But it's worth pausing on this idea because it reshapes how you think about interstellar distance. The 40 trillion kilometers to Proxima Centauri isn't a fixed obstacle with a single answer. It's a distance whose true difficulty depends entirely on how fast you're willing and able to go, and what that means for the people making the journey. This brings us to a very human question. If reaching another star realistically requires decades or centuries or millennia, how would we even attempt it? What would the people on such a mission actually experience? One of the most discussed ideas is the generation ship. The concept is exactly what it sounds like: a massive, self-sustaining spacecraft carrying not just a single crew, but successive generations of humans who live, grow up, have children, grow old, and die, all while the ship continues its multi-decade or multi-century journey toward its destination. The great-great-grandchildren of the original crew would be the ones who actually arrive. It sounds almost unbearable when you first hear it. An entire life lived inside a metal hull, hurtling through the dark, having never set foot on a planet, having never breathed unfiltered air, having never seen an unobstructed horizon. And yet, in some sense, it's not so different from how humans have always lived, bound within whatever environment, history, and circumstance handed us, building meaning, culture, and connection within those limits. A generation ship would need to be, in effect, a fully self-sufficient miniature biosphere, closed-loop life support systems capable of recycling air and water indefinitely, agricultural modules to grow food across generations, radiation shielding robust enough to protect inhabitants from cosmic rays over decades of exposure, a serious concern since interstellar space is bathed in high-energy particles that Earth's atmosphere and magnetic field normally shield us from. Social and psychological structures resilient enough to prevent the kind of internal conflict or despair that could unravel a community trapped together for generations with no possibility of leaving. Some researchers have proposed alternative approaches to sidestep the psychological burden of generation ships entirely. One of the most talked about is suspended animation, sometimes called hibernation or torpor-inducing technology. The idea is to significantly slow down human metabolism, perhaps by lowering body temperature, so that the crew essentially sleeps through most of the journey, aging minimally and waking only near the destination or during critical mission phases. NASA has actually funded early research into torpor-based space travel, inspired partly by the way some animals, like ground squirrels and certain bears, naturally enter states of dramatically reduced metabolic activity during hibernation. If humans could safely enter a similar state for extended periods, it could solve multiple problems at once. Less food and water needed, less psychological strain from years of confinement, and possibly reduced radiation sensitivity due to slowed cellular activity. It's still early experimental science. We are far from being able to safely place a human being into multi-year hibernation, but it's a genuinely active area of research, not idle speculation, and it points toward a future where interstellar travel might not require multiple generations of people living and dying aboard a ship, but rather a single crew, asleep for most of the voyage, waking to a sky full of unfamiliar stars. And then there's an idea that pushes even further into speculative territory, but one that serious thinkers in the field take seriously. What if the crew isn't biological at all? If artificial intelligence continues to advance the way it has over the past decade, it's entirely conceivable that the first true interstellar explorers won't be human beings, or even living creatures of any kind. They might be sophisticated robotic systems, autonomous, intelligent, capable of making decisions, adapting to unexpected circumstances, and operating for centuries without the fragility of a biological body. An AI-piloted probe wouldn't need food, wouldn't need air, wouldn't age in any meaningful biological sense, though its hardware would need protection from radiation and micrometeorite damage over the long haul. It could be put into low-power states for the bulk of the journey, conserving energy, and wake as it approached its destination, much like Voyager 1 itself, in a way though vastly more capable. Some researchers and futurists have gone even further, suggesting that if humanity ever manages to develop technology capable of scanning, mapping, or somehow encoding the essential patterns of human consciousness, the eventual colonists of other star systems might not be bodies at all, but digital minds transported at the speed of data, needing nothing more than energy and computational substrate to exist. This is deeply speculative, sitting at the outer edge of what's plausible, closer to philosophy than engineering. But it illustrates something important. Our idea of what it even means to travel to another star might look completely different a century or two from now than it does today. Whatever form it eventually takes, the honest truth is this: we are decades, at minimum, from having any of these technologies ready for a real mission. Breakthrough Starshot remains in early research phases, working through fundamental engineering challenges around sail materials, laser array construction, and miniaturized electronics. Nuclear thermal propulsion is being developed primarily for missions to Mars, not the stars. Fusion propulsion concepts like Daedalus remain largely theoretical, constrained by our still limited mastery of controlled fusion reactions even here on Earth. Antimatter production remains staggeringly expensive and inefficient, and hibernation technology for humans is still in the earliest stages of biological research. But here's what's genuinely exciting, and what I think gets lost sometimes in conversations about how far away all of this feels. Every single decade brings meaningful progress. Fusion research has made real strides in recent years. In December of 2022, scientists at the National Ignition Facility in California achieved what's called fusion ignition for the first time, producing more energy from a fusion reaction than was used to trigger it. That's not interstellar propulsion, but it's a genuine milestone on the long road toward mastering fusion. And mastering fusion is one of the key steps towards serious interstellar propulsion concepts. Materials science continues to advance at a rapid pace, producing lighter, stronger, more heat-resistant substances every year. The exact kind of innovation a light sail-based mission like Breakthrough Starshot desperately needs. Computing power continues to shrink in size while growing in capability, making it more plausible every year that a spacecraft the size of a postage stamp could carry meaningful sensors, processors, and communication equipment. None of this means interstellar travel is right around the corner. It isn't, but it means the story isn't static. It's a story that's actively being written, one incremental breakthrough at a time, by thousands of scientists and engineers across dozens of countries, most of whom will never see the final result of their work in their own lifetimes. And that's worth sitting with for a moment, because it means that working toward reaching the stars is in a very real sense an act of faith in the future, a belief that the effort matters even if you personally won't live to see it pay off. The engineers who built Voyager 1 in the 1970s knew it would likely be flying long after they were gone. They built it anyway, beautifully, meticulously, with golden records and hand-soldered circuits, because they believed the journey itself had value, independent of whether they'd ever see it reach the stars. That's the same spirit driving research into laser sails and fusion drives and hibernation technology today. Nobody currently working on Breakthrough Starshot expects to see a probe arrive at Proxima Centauri in their lifetime, even under the most optimistic scenarios. They're building the first steps of a staircase that other people, maybe their grandchildren, maybe people not yet born, will eventually climb the rest of the way. Because here's the truth. The value of asking how long would it take Voyager 1 to reach Proxima Centauri was never really about getting a precise number. It's about using that number as a mirror, a way of measuring ourselves against the true scale of the universe we live in. And once you hold that mirror up, something interesting happens. The number stops being depressing and starts being clarifying. Think about what it actually tells us. It tells us that the universe operates on timescales that make human civilization look like a single breath. It tells us that the vast majority of the cosmos will likely never be visited by anything we build, not because we lack ambition, but because the raw geometry of space is simply that enormous. And it tells us that despite all of this, despite the seemingly insurmountable scale of the challenge, we didn't just accept defeat. We built Voyager 1 anyway. We proposed Breakthrough Starshot anyway. We keep designing light sails and fusion drives and antimatter engines anyway, not because we expect to solve interstellar travel next year or even next century, but because the act of trying is itself meaningful. There's a concept in astronomy called the cosmic perspective, a term popularized by astrophysicist Neil deGrasse Tyson, though the underlying idea has been present in the writings of astronomers for generations. The cosmic perspective is the recognition that when you truly understand your place in the universe, how small you are, how brief your life is, how vast the distance is and how long the timescales, something paradoxical happens. Instead of feeling insignificant, many people report feeling more connected, more grateful, more aware of how extraordinary it is that any of this, stars, planets, life, consciousness, curiosity itself, exists at all. Consider the raw numbers one more time, not to feel crushed by them, but to feel awed by them. The universe is approximately 13.8 billion years old. Our sun and solar system formed about 4.6 billion years ago, out of the collapsed remnants of previous generations of stars. Stars that lived, burned through their nuclear fuel, and exploded, scattering heavy elements like carbon, oxygen, iron, and calcium across the galaxy. Every atom of calcium in your bones, every atom of iron in your blood, every atom of oxygen in the air you're breathing right now was forged inside the core of a star that existed and died long before our sun was born. That's not a metaphor. That's a literal, scientifically established fact. You are quite genuinely made of stardust, recycled material from stellar furnaces that operated billions of years before the Earth even existed. When you look up at Proxima Centauri, that faint red ember in the southern sky, you're looking at a star made of the same fundamental material that makes up your own body. Different arrangement, different history, but the same basic ingredients drawn from the same cosmic recycling process that has been running since the earliest generations of stars first lit up the young universe. This is where astronomy stops being purely about telescopes and spacecraft and starts becoming something closer to a form of self-understanding. Every question we ask about the universe, how far is that star? How old is that galaxy? Is there life on that planet? Is also, in a very real sense, a question about ourselves. Where did we come from? What are we made of? Are we alone? What is our story? And how does it fit into the much longer, much larger story of everything that exists? And that longer story is genuinely staggering when you lay it out. The universe began, as far as our best current science can determine, in an event known as the Big Bang, roughly 13.8 billion years ago, an expansion of space itself from an extraordinarily hot, dense state. For the first few 100,000 years, the universe was too hot for atoms to even form. It was an opaque plasma of charged particles. Then, as it expanded and cooled, atoms began to form, and light was finally able to travel freely, an event whose afterglow we can still detect today as the cosmic microwave background radiation, a faint hiss of ancient light that fills the entire sky. For hundreds of millions of years after that, the universe was dark. No stars yet existed to illuminate it. Then gravity did its slow, patient work, pulling together clouds of hydrogen and helium gas until they became dense and hot enough to ignite nuclear fusion. The very first stars were born, and in the cores of those stars, and in the explosive deaths of the largest among them, the periodic table as we know it began to take shape. Carbon, nitrogen, oxygen, silicon, iron, and eventually, after enough generations of stellar life and death, every element found on the periodic table today, galaxies formed, merged, grew. Our own Milky Way galaxy took shape over billions of years, eventually containing the hundreds of billions of stars we mentioned earlier, arranged in a vast spiral disk roughly 100,000 light-years across. And within that galaxy, in one of its outer spiral arms, roughly 26,000 light-years from the galactic center, our own solar system formed, not particularly special, not particularly central, just one ordinary planetary system among what is likely hundreds of billions throughout the galaxy alone. And on the third planet from an unremarkable yellow star, conditions happened to align in a way that allowed liquid water, a stable climate, and billions of years of relatively uninterrupted evolutionary time, ultimately giving rise to life, then complexity, then consciousness, then curiosity, then science, then telescopes, then spacecraft, then a species capable of calculating exactly how long it would take one of its machines to reach the very next star over. Let's bring this back down to something more concrete though, because cosmic perspective is powerful, but it shouldn't distract us from the genuinely fascinating engineering and scientific work happening right now, in our own lifetimes, aimed at closing that gap between 73,500 years and something more achievable. One of the most promising and frequently discussed concepts is nuclear fusion propulsion. Unlike the chemical rockets that got Voyager 1 off the ground, or even the ion thrusters used on some modern spacecraft, fusion propulsion would generate thrust by fusing light atomic nuclei, typically isotopes of hydrogen, like deuterium and tritium, releasing tremendous amounts of energy in the process. This is the same basic reaction that powers the Sun itself. If we could build a spacecraft engine that reliably harnesses controlled fusion and could do so efficiently enough to sustain thrust over long periods, we could theoretically reach speeds of 5 to 10% of the speed of light. At 10% of light speed, a trip to Proxima Centauri would take a little over 40 years, not a human lifetime spent entirely in transit, but well within the range of a single career, or a mission a young astronomer could realistically hope to see the results of. This isn't pure fantasy either. Serious engineering studies have explored this exact concept. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, proposed a fusion-powered starship designed specifically to reach a nearby star system within a human lifetime, using pulsed fusion detonations for propulsion, not entirely unlike a controlled series of small thermonuclear explosions directing energy out the back of the spacecraft. It was a theoretical study, not a construction plan, but it demonstrated that the physics, at least on paper, wasn't the limiting factor. Engineering, materials science, and fuel production were, and in many ways, still are. There's also Project Icarus, a modern successor study launched in the 2010s that revisited and updated the Daedalus concept, using more current scientific understanding and technology assumptions. Researchers involved in Icarus have continued to explore whether fusion propulsion could be made more practical, more fuel-efficient, and safer, refining the original 1970s blueprint with decades of additional knowledge about materials, plasma physics, and fusion confinement. Then there's antimatter propulsion, which sits even further out on the frontier of theoretical physics, but which offers an intriguing promise. When matter and antimatter collide, they annihilate each other completely, converting 100% of their mass into pure energy. According to Einstein's famous equation, energy equals mass times the speed of light squared. This is, in principle, the most efficient possible way to convert mass into propulsive energy, far more efficient than fusion, which only converts a small fraction of the reacting mass into energy. The catch, and it's an enormous catch, is that antimatter is almost unimaginably difficult and expensive to produce. Current facilities, like the ones at CERN, can produce antimatter, but only in quantities measured in nanograms, at a cost that would make a single gram of antimatter worth more than the entire global economy many times over if produced at current rates and prices. Scientists have calculated that producing even a single gram of antimatter using current technology would take enormous amounts of energy and an impractically long time. So while antimatter propulsion remains a favorite of science fiction and a legitimate subject of serious theoretical physics papers, it exists firmly in the realm of maybe someday, with technology we can't currently imagine, rather than anything on a foreseeable engineering roadmap. Somewhere between the extremes of achievable within decades and theoretically possible but wildly impractical sits the light sail concept we touched on earlier with Breakthrough Starshot. This approach sidesteps the fuel problem entirely by not carrying fuel at all. Instead, the spacecraft, really more of a tiny ultra-lightweight probe, potentially just a few grams in mass, attached to a large, ultra-thin reflective sail, gets pushed forward by the momentum of photons either from sunlight or, more powerfully, from a massive ground-based or space-based laser array specifically built to accelerate it. Breakthrough Starshot, announced in 2016, with backing from physicist Stephen Hawking, Facebook founder Mark Zuckerberg, and Russian entrepreneur Yuri Milner, proposed exactly this: an array of powerful lasers on Earth, focused with extreme precision on a fleet of tiny light-sail probes, accelerating them to roughly 20% of the speed of light, within just a few minutes of sustained laser pushing. At that speed, reaching Proxima Centauri would take a little over 20 years, plus another 4 years for any signal or data sent back to reach Earth, meaning a total mission timeline from launch to receive data of around 25 years. Slow by the standards of a single human impatience, but staggeringly fast by the standards of interstellar travel, and crucially, within a plausible human lifetime, and even within range of realistic long-term institutional planning. The challenges facing Breakthrough Starshot are still immense. Building a laser array powerful enough, potentially requiring gigawatts of sustained power output, focused with extraordinary precision across vast distances, is itself a massive engineering undertaking that doesn't yet exist. The probes themselves would need to survive the intense acceleration, the radiation environment we discussed earlier, and the risk of dust collisions, all while carrying instruments sensitive enough to gather meaningful scientific data and transmit it back across 4 light-years using an antenna that, by necessity, would have to be almost comically small and lightweight. But unlike antimatter propulsion, this isn't science fiction dressed up as a serious concept. It's an active area of ongoing research with real funding, real published papers, and real incremental progress. It represents, probably more than any other concept currently on the table, our actual best shot, pun very much intended, at sending something to another star system within a time frame that matters to us as individuals, rather than as a species spanning tens of thousands of years. Beyond propulsion technology, there's an entirely different category of solution to the interstellar travel problem. Instead of making the trip faster, we make ourselves capable of enduring a longer trip. This is where concepts like generation ships and suspended animation enter the conversation. A generation ship is exactly what it sounds like: a massive, self-sustaining spacecraft designed to support not just the astronauts who launch, but their children, grandchildren, and great-grandchildren across a journey that might take centuries. The people who arrive at Proxima Centauri b, in this scenario, would never be the same people who left Earth. They'd be descendants born and raised entirely within the confines of the ship, having never seen an open sky or felt planetary gravity until the moment of arrival. This raises questions that go well beyond engineering. How do you design a closed ecological system that can reliably produce food, recycle water and air, and maintain a stable environment for hundreds of years without any resupply from Earth? How do you preserve knowledge, culture, and purpose across multiple generations who never chose the mission themselves? How do you prevent genetic problems from a limited breeding population, or psychological strain from generations of people living in permanent confinement? These aren't hypothetical afterthoughts. They're central design problems that researchers studying generation ship feasibility, including groups like the Icarus Interstellar Organization, have spent considerable effort trying to address. Suspended animation offers a different angle on the same basic problem. Rather than living through the entire journey, what if the crew simply slept through most of it? This idea, often called cryosleep or hibernation travel in science fiction, has some basis in real biological research. Scientists have studied torpor, a natural hibernation-like state used by animals like ground squirrels and bears to survive winters with drastically reduced metabolic activity, as a potential model for inducing something similar in humans during long space flights. NASA has actually funded early-stage research into human torpor for potential use on multi-year Mars missions, let alone multi-decade interstellar ones. The idea would be to lower a crew member's body temperature and metabolic rate significantly, reducing their need for food, water, and even psychological engagement over long stretches, and then reviving them as the ship approaches its destination. The technology for reliably and safely inducing torpor in humans for years or decades at a time doesn't exist yet, and there are serious open questions about muscle atrophy, bone density loss, cognitive effects, and long-term organ health during extended hibernation. But it remains a subject of genuine scientific research rather than pure speculation, and it's one of the more plausible bridges between the trip takes too long for a human lifetime and the trip is survivable. There's an even more speculative, more philosophically loaded idea that occasionally surfaces in these discussions. What if we didn't send humans at all, at least not in biological form? What if instead we sent digitized human minds or advanced artificial intelligence systems capable of representing human knowledge, curiosity, and decision-making stored in extremely durable, radiation-hardened computer systems? Such a probe wouldn't need food, air, or gravity. It wouldn't age in any meaningful biological sense. It could, in principle, simply wait out the decades or centuries of transit time in a low-power state and wake up, however you want to define that for a digital system, upon arrival. This concept sits at the intersection of interstellar travel and questions we don't yet know how to answer about consciousness, identity, and what it would even mean to be a digitized mind. Is a perfect digital copy of your memories and thought patterns actually you, or is it a separate entity that merely believes itself to be you? These are genuinely unresolved philosophical questions, not just technical ones, and they intersect with ongoing, very real research into brain mapping, neural interfaces, and artificial general intelligence happening today. Whatever the eventual answer, the interesting through line connecting fusion drives, light sails, generation ships, hibernation research, and speculative digital minds is this: they all represent different strategies for solving the exact same underlying problem highlighted by that Voyager 1 calculation, the problem of a universe that is simply too big and too governed by the speed of light for our current transportation methods to handle. Every one of these approaches is, in its own way, an attempt to bend the rules of that 73,500-year number, whether by going faster, living longer, sleeping through it, or transforming what we even means as travelers. Let's shift gears now and talk about something a little more grounded. What we can actually observe and learn about Proxima Centauri and its planetary system using instruments we already have right now, without needing to send anything there at all. Because even though physically traveling to another star system remains, for the foreseeable future, an almost impossibly distant goal, our ability to study these systems remotely has advanced at an extraordinary pace over the past 2 decades. Proxima Centauri b, the planet we mentioned earlier orbiting within Proxima Centauri's habitable zone, was discovered in 2016 by a team of astronomers using the European Southern Observatory's telescopes in Chile, employing a technique called the radial velocity method. This method doesn't directly see the planet at all. Instead, it detects the tiny gravitational wobble that an orbiting planet induces on its host star, a slight periodic shift in the star's light spectrum caused by the star being tugged slightly back and forth as the planet orbits it. By carefully measuring these shifts over time, astronomers can infer the presence of a planet, estimate its minimum mass, and calculate its orbital period with remarkable precision, all without ever capturing a single photon of light actually reflected off the planet itself. Proxima Centauri B's orbital period turns out to be just 11.2 Earth days, meaning a full year on that planet lasts less than 2 of our weeks. This is because Proxima Centauri, being a red dwarf star, is much smaller, cooler, and dimmer than our Sun, so its habitable zone, the region where temperatures could theoretically allow liquid water to exist on a planet's surface, sits much closer to the star than Earth's distance from the Sun. Proxima Centauri b orbits at roughly 7.5 million kilometers from its star, which is about 20 times closer than Earth orbits the Sun, yet still receives roughly comparable levels of stellar energy because Proxima Centauri itself puts out so much less total light and heat. This proximity, however, creates its own serious problems for the possibility of life. Being that close to a red dwarf star means Proxima Centauri b is almost certainly tidally locked, meaning one side of the planet permanently faces the star, much like how our moon always shows the same face to Earth, while the other side remains in permanent darkness. This creates extreme temperature differences between the day side and night side, potentially resulting in ferocious winds as atmosphere, if any exists, tries to circulate heat from one side to the other. Even more concerning, red dwarf stars like Proxima Centauri are known for producing intense and frequent stellar flares, sudden, dramatic bursts of radiation and charged particles far more energetic relative to the star's size than anything our own Sun produces. In March of 2017, astronomers observed Proxima Centauri emit a flare so powerful that it briefly increased the star's brightness by a factor of 1,000, and researchers have calculated that flares of this intensity could potentially strip away a significant portion of any atmosphere on a closely orbiting planet like Proxima Centauri b, and could deliver radiation doses to any surface unshielded by a strong magnetic field that would be lethal to most known forms of life. This doesn't necessarily rule out the possibility of life on Proxima Centauri b entirely. Life on Earth has proven remarkably resilient in extreme environments, from deep-sea hydrothermal vents to Antarctic ice to highly acidic hot springs, and it's possible that life elsewhere could similarly adapt to harsh conditions we might initially assume to be sterile. But it does mean that Proxima Centauri b is far from a guaranteed second Earth, and any serious scientific assessment of its habitability has to grapple honestly with these significant challenges. Interestingly, Proxima Centauri b isn't the only planet discovered in that system. In 2019 and 2020, follow-up observations using even more sensitive instruments revealed hints of a second planet, tentatively named Proxima Centauri c, orbiting much further out, roughly 1.5 astronomical units from the star, farther than Earth orbits the Sun, though because Proxima Centauri is so much dimmer than our Sun, this planet, if confirmed, would still be quite cold. And in 2022, astronomers using the European Southern Observatory's advanced instruments announced the discovery of yet another candidate, Proxima Centauri d, an even smaller planet orbiting extremely close to the star, with an orbital period of just about 5 days. If all 3 planets are eventually confirmed with high confidence, Proxima Centauri would host a genuine multi-planet system, quite unlike the picture many people carried in their heads even a decade ago, when the very concept of planets around other stars was still a relatively fresh and thrilling discovery rather than an almost routine finding. Let's dive deeper into the observational astronomy side of this story, because the tools and techniques astronomers use to study Proxima Centauri and other nearby star systems represent some of the most impressive engineering achievements of the past few decades. and they deserve a much closer look than a passing mention. The radial velocity method we touched on briefly relies on something called the Doppler effect, the same physical principle that causes an ambulance siren to sound higher pitched as it approaches you and lower pitched as it moves away. Light behaves in an analogous way. When a star moves toward an observer, its light waves get compressed, shifting slightly toward the blue end of the spectrum, and when it moves away, the light waves stretch out, shifting toward the red end. As a planet orbits a star, its gravity causes the star to move in a small circular or elliptical path around their shared center of mass, a point called the barycenter. From Earth, we can't directly observe this tiny wobble as a visible motion, but we can detect it through incredibly precise measurements of the star's spectral lines shifting back and forth in a repeating pattern. The instruments capable of doing this with the necessary precision are marvels of engineering in their own right. The HARP spectrograph, high-accuracy radial velocity planet searcher, mounted on a telescope at the European Southern Observatory's La Silla site in Chile, was specifically designed to detect radial velocity shifts as small as about 1 meter per second. To put that in perspective, that's roughly the speed of a brisk walk, and HARPs can detect that tinier change in a star's velocity from a distance of trillions of kilometers away. Its successor, Espresso, installed at the Very Large Telescope in Chile, pushes this precision even further, aiming for velocity sensitivities down to around 10 centimeters per second under ideal conditions, slower than most people crawl. This level of precision is what allowed astronomers to detect Proxima Centauri b in the first place, despite the planet itself never being directly imaged. The star's tiny wobble, caused by the gravitational tug of a planet with roughly 1.3 times the mass of Earth, was detectable because these instruments had been refined over years of careful engineering, calibration, and painstaking data analysis, often combining years or even decades of repeated observations to filter out noise and confirm that a genuine periodic signal was present, rather than some artifact of stellar activity or instrumental error. This last point matters more than people often realize. Red dwarf stars like Proxima Centauri are known for something astronomers call stellar activity noise, star spots, flares, and other surface phenomena that can create radial velocity signals that mimic the presence of a planet, or that can obscure a real planetary signal within a noisy background. Distinguishing a genuine planet from this kind of stellar noise requires careful statistical modeling, multiple independent lines of evidence, and often years of follow-up observations before a discovery can be confidently confirmed. This is part of why Proxima Centauri C and D took additional years of observation beyond the initial detection of Proxima Centauri b to be proposed and refined, and why some exoplanet candidates around other stars remain in a kind of scientific limbo for years, neither fully confirmed nor definitively ruled out. Beyond radial velocity, astronomers use several other complementary techniques to study exoplanets, each with its own strengths and limitations. The transit method, made famous by NASA's Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, or TESS, detects planets by measuring the tiny periodic dimming of a star's light as a planet passes directly in front of it from our vantage point on Earth. This method has been enormously productive, responsible for the discovery of thousands of exoplanets, because it can be applied systematically to huge numbers of stars simultaneously, simply by monitoring their brightness continuously and looking for repeating dips. However, the transit method only works when a planet's orbital plane happens to be aligned in just the right way relative to Earth, so that it actually passes in front of its star from our perspective. For Proxima Centauri b, this alignment doesn't appear to occur, or at least hasn't been confirmed, which is why its discovery relied on radial velocity data instead. This orbital alignment issue is a significant limitation of the transit method in general. Astronomers estimate that only a small percentage of exoplanets are oriented favorably enough for transits to be observable from Earth, meaning the transit method, despite its enormous productivity, is still only catching a fraction of the planets that are actually out there. Direct imaging represents yet another approach, and arguably the most conceptually satisfying one, since it involves actually capturing photons of light reflected or emitted by the planet itself, rather than inferring its presence indirectly. But direct imaging is extraordinarily difficult because planets are incredibly faint compared to the stars they orbit, often many billions of times fainter, and they're located at angular separations from their stars that are, from Earth's perspective, absurdly tiny even for relatively nearby systems. Special techniques like coronagraphy, which uses a physical or digital mask to block out the overwhelming glare of the host star, allow astronomers to occasionally spot planets directly, particularly large, young, hot planets that still glow with residual heat from their formation, orbiting relatively far from their host stars. The James Webb Space Telescope, launched in December of 2021, has direct imaging capabilities that have already produced some remarkable results, capturing actual images of exoplanets in nearby systems, showing them as faint points of light distinguishable from the glare of their parent stars. For Proxima Centauri's planets specifically, direct imaging remains extremely challenging, given how close the planets orbit to their dim host star and how small they are. But ongoing and future instruments, including next-generation ground-based telescopes like the extremely large telescope currently under construction in Chile, are expected to push the boundaries of what's directly observable, potentially allowing astronomers to capture actual images, or at least much more detailed spectroscopic data from planets in our nearest neighboring star system within the coming decade or two. Speaking of spectroscopy, this brings us to perhaps the most exciting frontier in exoplanet science right now: atmospheric characterization. Once a planet is known to exist and its basic orbital parameters are established, the next major scientific question becomes: what, if anything, is actually happening on that planet's surface and in its atmosphere? Does it have an atmosphere at all? What gases make it up? Are there any potential biosignatures, chemical signals that might indicate the presence of biological processes? Spectroscopy allows astronomers to answer some of these questions by analyzing how light interacts with a planet's atmosphere, either through transmission spectroscopy, which examines starlight filtering through a planet's atmosphere during a transit, or through emission spectroscopy, which studies the planet's own thermal radiation. Different molecules absorb and emit light at very specific, characteristic wavelengths, creating a kind of chemical fingerprint that astronomers can read in the light they collect. Water vapor, carbon dioxide, methane, and oxygen all have distinctive spectral signatures, and detecting the right combination of these gases in the right relative abundances could provide compelling, though not necessarily conclusive, evidence that a planet's atmosphere is being actively maintained or altered by biological processes rather than purely geological or chemical ones. The James Webb Space Telescope has already begun applying these techniques to exoplanets, and while Proxima Centauri b currently isn't confirmed to transit its star from our perspective, which would be necessary for the most common transmission spectroscopy technique to work, researchers continue to explore alternative methods, and future instruments specifically designed for direct spectroscopic analysis of non-transiting planets around nearby stars are actively being developed and proposed. One such ambitious future concept is NASA's Habitable Worlds Observatory, a proposed space telescope intended to directly image and spectroscopically analyze potentially habitable exoplanets around nearby stars, including systems like Alpha Centauri and Proxima Centauri, though still in the conceptual and early planning stages as of the mid-2020s, with an anticipated launch sometime in the 2040s if development proceeds on schedule. This mission represents one of the most direct and promising paths toward actually answering the question of whether Proxima Centauri b, or planets in similar nearby systems, might harbor detectable signs of life, all without needing to physically travel there at all. It's worth pausing on this point, because it underscores something important about the whole discussion of interstellar travel we've been having throughout this conversation. Even in a universe where physically traveling to another star system remains a monumental challenge measured in decades, centuries, or even the tens of thousands of years suggested by that original Voyager calculation, our ability to study these distant worlds from right here on Earth or from telescopes in Earth's orbit continues to advance rapidly. We may well know within the coming few decades whether Proxima Centauri b or its neighboring planets show promising atmospheric signatures suggestive of habitability or even biological activity, long before any spacecraft, light sail or otherwise, could possibly arrive to confirm it directly. This creates an interesting tension in how we think about our exploration of the cosmos. Remote observation can tell us an enormous amount, potentially even suggesting the presence of life, but it can't provide the kind of direct, hands-on confirmation that a probe, rover, or eventually human explorers could offer. There's a difference between detecting an intriguing spectroscopic signature from 4 light-years away and actually being able to sample a planet's atmosphere, examine its surface geology, or, in the most exciting hypothetical scenario, directly study alien biology. Astronomy and interstellar travel, in this sense, aren't competing approaches to the same problem. They're complementary phases of a much longer scientific journey where remote observation tells us where to look, what to prioritize, and what mysteries are worth the enormous effort of eventually sending something there in person. Let's turn our attention now to a topic that's been implicit throughout much of this discussion, but deserves direct treatment. The question of what would actually happen if a probe, whether a breakthrough Starshot-style light sail or some more advanced future spacecraft, actually arrived at Proxima Centauri after its multi-decade or multi-century journey. What would it need to accomplish? How would it communicate its findings back to Earth? And what unique engineering challenges does the arrival phase of an interstellar mission present that are just as demanding, in their own way, as the challenges of getting there in the first place? Consider first the sheer velocity problem. A light sail probe accelerated to 20% of the speed of light, as envisioned by the breakthrough Starshot concept, would be traveling at roughly 60,000 kilometers per second when it reaches the Proxima Centauri system. At that speed, there is no conceivable way, using any propulsion technology remotely near our current or near future capability, to decelerate the probe and place it into a stable orbit around Proxima Centauri b or any other planet in the system. The probe would necessarily execute what's called a flyby, zooming past its target at extraordinary velocity, with the entire encounter, from first approach to departure, lasting mere minutes or even seconds, depending on how close the flyby path takes it to the planet. This creates an enormously demanding engineering challenge, cramming everything the mission wants to accomplish: imaging, spectroscopic analysis of the planet's atmosphere, magnetic field measurements, particle detection, and any other scientific goals, into an observation window measured in seconds rather than the days, weeks, or months that orbital missions typically enjoy. Every instrument would need to be fully autonomous, since there's no possibility of real-time control from Earth Given the 4-plus-year communication delay each way, and every single measurement would need to be pre-programmed with extraordinary precision, timed to the exact moment the probe passes closest to its target, all while the spacecraft itself endures extreme velocities, is exposed to whatever radiation environment exists in that system, and must accurately point its instruments and antenna, despite tiny gram-scale mass and enormous velocity, akin to threading a needle while moving faster than any human-made object has ever traveled. This is where the swarm concept, mentioned earlier as part of Breakthrough Starshot strategy, becomes particularly important. Rather than sending a single light sail probe and hoping everything works perfectly during its brief flyby, mission planners have proposed launching dozens or even hundreds of individual gram-scale probes in a coordinated fleet, spread out spatially and temporally. This redundancy serves multiple purposes. It protects against individual probe failures, whether from manufacturing defects, collision with interstellar dust particles during the multi-year transit, or malfunction during the critical flyby moment. It also allows for a kind of distributed observation strategy, where different probes within the swarm might pass the target planet at slightly different distances and angles, providing multiple, complementary datasets that combined together could offer a far richer picture of the system than any single probe could achieve alone. Communication represents perhaps the most underappreciated challenge of this entire endeavor. A probe massing only a few grams, powered by a small onboard battery, or perhaps a tiny radioisotope power source, would have access to only a minuscule amount of electrical power for its transmitter, nowhere near what's needed to broadcast a strong signal across 4.24 light-years back to Earth. The proposed solution involves using extremely tight, laser-based communication beams rather than traditional radio broadcasts, since a focused laser can concentrate a given amount of transmission power into a much narrower beam, allowing more of that power to actually be detected at the receiving end. Compared to a radio signal that spreads out in all directions, even with this laser communication approach, the received signal at Earth would be almost unimaginably faint, requiring an array of large, sensitive telescopes on Earth's surface, likely working in combination to detect and decode the transmitted data, and even under best-case assumptions, the data rate, the actual amount of information that could be reliably transmitted per second, would be extremely low, perhaps just a handful of bits per second, meaning that even a modest amount of scientific data, such as a single low-resolution image or a basic spectroscopic reading, could take hours, days, or potentially even longer to fully transmit back to Earth, on top of the 4+ years the signal itself takes to physically travel the distance at the speed of light. This means that mission planners would need to think very carefully about what data is worth prioritizing for transmission, given these severe bandwidth constraints. A full high-resolution color image of the kind we're accustomed to seeing from missions like the Mars rovers or the James Webb Space Telescope would likely be entirely impractical to transmit from an interstellar probe under current or near-future technological constraints. Instead, mission designers would likely prioritize highly compressed data, low-resolution imagery, or specific targeted scientific measurements, perhaps a spectroscopic reading confirming or ruling out the presence of specific atmospheric gases, or basic photometric data confirming a planet's size, reflectivity, and surface temperature variations, rather than attempting to capture and transmit anything resembling the rich, detailed imagery that captures public imagination in artistic renderings of these missions. There's also the question of what instruments a probe should actually carry, given the severe mass constraints imposed by the physics of the light sail acceleration process itself. Remember that the entire premise of achieving speeds up to 20% of light speed relies on keeping the probe's total mass down to just a few grams. This leaves precious little room for traditional scientific instruments, which, even when heavily miniaturized, still require some minimum mass and power budget to function. Cameras, spectrometers, magnetometers, and particle detectors would all need to be radically redesigned and miniaturized far beyond what's currently achievable, likely relying on advances in nanotechnology, integrated photonics, and extremely low-power electronics that don't yet exist in mature flight-ready form. This is actually one of the more underappreciated aspects of the Breakthrough Starshot program's research agenda. A significant portion of the engineering effort isn't focused on the propulsion system at all, but rather on developing what the program's researchers sometimes call wafer-scale spacecraft, essentially entire functioning spacecraft, complete with cameras, communication systems, navigation sensors, and power sources integrated onto a single small chip or wafer, weighing only a gram or so in total. This pushes the boundaries of integrated circuit design, low-power computing, and miniaturized optics in ways that have applications well beyond interstellar travel, potentially benefiting fields like medical implants, environmental sensing, and even conventional satellite technology. Long before any interstellar mission actually launches, navigation presents yet another significant challenge for these hypothetical arrival scenarios. A probe traveling at relativistic speeds needs to know, with extraordinary precision, exactly where it is and exactly where its target is, in order to properly orient its instruments during the brief flyby window and to aim its communication laser accurately back toward Earth afterward. But navigation systems that work well within our solar system, relying on known reference points and communication with Earth-based tracking stations, become far less reliable across interstellar distances, especially for a tiny probe without the luxury of onboard nuclear-powered radioisotope thermoelectric generators providing steady long-term power for sophisticated navigation computers. Proposed solutions include using pulsars, rapidly rotating neutron stars that emit extremely regular, precisely timed pulses of radiation, as a kind of cosmic GPS system, since their pulse timing is so consistent and well documented that a probe could theoretically determine its position in the galaxy by comparing the arrival times of pulses from several different known pulsars, a concept that's actually already been tested experimentally on spacecraft within our own solar system, including a NASA demonstration mission called Station Explorer for X-ray timing and navigation technology, launched in 2017. All of this illustrates something important about the nature of interstellar exploration as a scientific and engineering endeavor. It's not simply a matter of building a sufficiently powerful engine and pointing a spacecraft in the right direction. Every single phase of such a mission, launch, acceleration, the long cruise phase, arrival, data collection during an impossibly brief flyby window, and the transmission of results back across trillions of kilometers, presents its own distinct, formidable set of challenges, many of which require entirely new technologies that don't yet exist, and some of which push against fundamental physical limits that may never be fully overcome, only worked around through clever engineering compromises. Now let's turn to a different but closely related dimension of this whole topic: the enormous economic and political questions that surround any serious attempt at interstellar travel. Because even if every single technical hurdle we've discussed so far were somehow solved, the question of who actually pays for such an undertaking, why they would choose to do so, and how such a project could be sustained across the multi-decade or even multi-generational timescales involved, represents its own profound challenge, arguably just as difficult as the physics and engineering itself, Breakthrough Starshot, the real-world initiative most closely aligned with the light sail concept we've discussed throughout this conversation, was launched in 2016 with an initial funding commitment of $100 million from the Breakthrough Initiatives, a science funding program established by the Russian-born billionaire Yuri Milner. That initial sum, while substantial by the standards of most privately funded scientific research programs, is understood by essentially everyone involved with the project to represent only the earliest, most preliminary phase of research and development, essentially seed funding intended to explore basic feasibility questions rather than anything close to what would be required to actually design, build, test, and launch a functioning interstellar probe swarm. Realistic estimates for the full cost of a mission along the lines of what Breakthrough Starshot envisions, including the ground-based or space-based laser array needed to accelerate the sails, the manufacturing of hundreds of individual probes, the extensive testing required to validate the entire system, and the deep space communication infrastructure needed to receive data back from the mission decades later, run into the tens of billions of dollars, and some more conservative estimates suggest the true cost could exceed $100 billion once all necessary supporting infrastructure and decades of sustained research and development are accounted for. To put that figure in perspective, it's worth comparing it to costs associated with other major space exploration efforts humanity has undertaken. NASA's Apollo program, which successfully landed humans on the Moon between 1969 and 1972, cost approximately $150 billion in inflation-adjusted terms, spread across roughly a decade of intensive development. The International Space Station, a collaborative project involving multiple national space agencies, has cost more than $150 billion cumulatively since construction began in 1998, a cost shared among the participating nations and spread out over more than 2 decades. These comparisons suggest that a serious, comprehensive interstellar mission wouldn't necessarily be unprecedented in scale compared to humanity's past major space endeavors, but it would still require an extraordinary, sustained political and financial commitment, likely spanning multiple decades before any results at all could be expected, given the multi-year construction timeline for necessary infrastructure, followed by decades of travel time, followed by years more for data to be transmitted back to Earth after arrival. This timescale creates a unique challenge that most large-scale human projects don't typically face. An interstellar mission would almost certainly outlive the political administrations, corporate leadership structures, and even the individual scientists and engineers who initiated the project. Consider that if a mission using current light sail concepts launched today and took, say, 20 years to reach even a substantial fraction of light speed given realistic engineering constraints, and then required over 20 additional years of travel time to reach Proxima Centauri, followed by more than 4 years for the return signal to arrive, the earliest possible confirmation of successful data return would come roughly 45 to 50 years after the mission's initial launch. Anyone born today in 2026, involved in the earliest planning stages of such a mission as a young graduate student or junior engineer, would likely be well into their 70s by the time any actual results came back, assuming the mission succeeded on the first attempt. This raises profound questions about institutional continuity that go well beyond pure engineering. How do you structure a scientific and engineering organization to maintain consistent funding, technical expertise, and institutional memory across a 50-year-plus horizon, particularly when the project's founding personnel will inevitably retire and in many cases pass away long before the mission's ultimate success or failure becomes known. Historical precedents for this kind of extreme long-term institutional planning are relatively rare, but not entirely absent. Large scientific collaborations like the ones responsible for building and operating gravitational wave observatories, or the multi-decade planning processes behind major space telescopes, offer at least partial models, though even these examples typically involve timescales of years or a couple of decades, rather than the 50-plus year commitment a genuine interstellar mission would likely require. Some researchers and futurists studying this problem have proposed models drawing on historical examples of extremely long-term human projects, like medieval cathedral construction, which sometimes took generations to complete, with the original architects and craftspeople who laid the foundation stones never living to see the finished building, yet successfully passing along enough institutional knowledge, documentation, and cultural commitment to the project that subsequent generations of workers were able to complete the vision. Whether modern scientific and engineering institutions operating within the political and economic pressures of contemporary democratic societies and quarterly focused corporate structures could sustain a similarly multi-generational commitment to a project without any guaranteed payoff for 50 years or more remains a genuinely open and difficult question. This is where the involvement of private philanthropic funding, of the kind Yuri Milner has provided through the Breakthrough initiatives, becomes particularly interesting to consider, because private philanthropic and scientific foundations sometimes have more flexibility to commit to extremely long-term projects without the same political pressures that affect government-funded space agencies, which typically face election cycles, changing administrations, and shifting budget priorities every few years. However, private philanthropic funding also carries its own risks and limitations. Individual billionaires or private foundations can change their priorities, face financial reversals, or simply lose interest over time in ways that might be less likely, though certainly not impossible, for a well-established government agency with decades of institutional continuity like NASA or the European Space Agency. There's also a compelling argument to be made that a project of this magnitude and scientific significance would benefit enormously from genuine international collaboration, spreading both the financial burden and the technical expertise across multiple nations and institutions, similar to how the International Space Station or the Large Hadron Collider at CERN involved contributions and expertise from dozens of countries working together toward a shared scientific goal. International collaboration on this scale also offers a kind of institutional resilience, even if one participating nation's political priorities shift or one nation's funding commitment wavers due to domestic economic pressures. A sufficiently broad international coalition might be able to absorb that setback and continue the project, rather than seeing the entire effort collapse due to the political whims of any single funding source. That said, international collaboration on this scale also introduces its own complications, particularly around questions of technology sharing, intellectual property, and geopolitical tensions. Some of the underlying technologies relevant to a mission like this, extremely powerful laser arrays, in particular, have obvious potential dual-use applications in military contexts, since a laser array capable of pushing a light sail to a meaningful fraction of the speed of light could, in principle, also serve as an incredibly powerful directed energy weapon, at least in theory, raising legitimate concerns among national governments about sharing this kind of technology openly across international borders, particularly given current geopolitical tensions between major world powers. This dual-use concern isn't merely hypothetical or paranoid speculation, it's a real consideration that arises whenever advanced laser technology, capable of concentrating enormous amounts of energy onto a small target from a great distance, is discussed in any context, whether for genuinely peaceful scientific purposes like interstellar propulsion or otherwise. Any serious international collaboration on breakthrough Starshot-style laser propulsion technology would need to grapple honestly with these dual-use concerns, likely requiring careful diplomatic negotiation, transparency measures, and possibly formal international agreements or treaties governing the technology's development and deployment, not unlike the international frameworks that currently govern nuclear technology or certain categories of advanced weaponry. Beyond the purely financial and political dimensions, there's also a fascinating question of motivation. Why would any government, corporation, or coalition of nations actually choose to invest tens or potentially hundreds of billions of dollars into a project whose payoff, in terms of concrete scientific results, wouldn't materialize for 50 years or more, especially when that same money could instead be directed toward more immediate, tangible priorities like addressing climate change, improving public health infrastructure, or funding near-term space exploration efforts within our own solar system that would produce results within a few years rather than a few generations. This is a genuinely difficult question without an easy or universally satisfying answer, but history offers some useful perspective. Humans have, throughout history, repeatedly chosen to invest enormous resources into projects whose payoffs were distant, uncertain, or primarily symbolic and inspirational rather than immediately practical, from the aforementioned cathedral-building projects of medieval Europe to the space race of the 1960s, which was driven as much by geopolitical prestige and national identity as by any concrete practical necessity, to modern fundamental physics research like the search for gravitational waves or the hunt for the Higgs boson, both of which required decades of sustained investment before producing any confirmed results, and neither of which offered any immediate practical application at the time the investment decisions were made. Proponents of interstellar exploration often argue that the psychological, cultural, and inspirational value of such a project, demonstrating humanity's capacity for extraordinarily ambitious, long-term cooperative achievement, and potentially answering one of the most profound questions our species has ever asked, whether we are alone in the universe, represents a form of value that, while difficult to quantify in purely economic terms, is nonetheless real and significant, comparable in some ways to the broader cultural and scientific value that humanity's moon landings provided, well beyond their immediate practical or military applications during the Cold War era. Let's shift now to exploring some of the alternative propulsion concepts that go beyond the light sail approach we've focused on so far, because breakthrough Starshot's laser-driven sail is really just one proposed solution among many that researchers have seriously considered over the decades, each with dramatically different engineering trade-offs, timescales, and levels of technological maturity. Nuclear pulse propulsion represents one of the oldest and, in some ways, most technically mature alternative concepts, dating back to a 1950s and 60s research effort called Project Orion, led by physicist Freeman Dyson, among others, working under contract with the United States government. The basic concept involves detonating a series of small nuclear explosive devices behind a spacecraft equipped with a massive pusher plate and sophisticated shock-absorbing system, with each detonation providing a powerful incremental thrust impulse. While this might sound almost cartoonishly dangerous, and it does raise obvious concerns around nuclear fallout, radiation exposure, and the political complications of launching nuclear devices into space, the physics behind it is actually reasonably sound, and some later theoretical extensions of this concept, including a more refined 1970s design study called Project Daedalus, conducted by the British Interplanetary Society, envisioned using controlled nuclear fusion pulse propulsion rather than fission-based nuclear explosives to achieve speeds of around 12% of the speed of light, sufficient to reach a nearby star system within roughly 50 years. Project Daedalus specifically was designed as an unmanned probe mission intended to reach Barnard's star, located about 6 light-years from Earth, which at the time of the study's design in the mid-1970s was believed to potentially host a planetary system, though later, more precise observations have cast doubt on this original assumption. The Daedalus design called for an enormous spacecraft, weighing nearly 54,000 tons at launch, the vast majority of that mass consisting of nuclear fusion fuel pellets that would be sequentially detonated behind the spacecraft to provide propulsion, a design that starkly illustrates just how much propellant mass is required to achieve relativistic speeds using this approach, compared to the ultra-lightweight light sail concept that requires essentially no onboard propellant mass at all, relying instead on an external Earth-based laser array for its propulsive energy. This propellant mass problem is actually one of the most fundamental challenges in all of rocket propulsion, formalized mathematically by what's called the Tsiolkovsky rocket equation, named after the Russian rocket scientist Konstantin Tsiolkovsky, who first derived it in the late 19th century. Without diving too deeply into the mathematics, the core insight of this equation is that the amount of propellant a spacecraft needs to achieve a given change in velocity increases exponentially, not linearly, as the desired velocity change increases, meaning that reaching extremely high velocities using traditional propulsion methods that carry their own reaction mass requires disproportionately, almost absurdly, large amounts of fuel, quickly reaching a point of severely diminishing returns where adding more fuel mass to the spacecraft actually becomes counterproductive, since that additional fuel mass itself then needs to be accelerated too. This is precisely the mathematical reality that makes the light sail concept so appealing from a pure physics perspective, because the propulsive energy comes from an external source, the enormous laser array remaining on Earth or in Earth orbit. The spacecraft itself doesn't need to carry any propellant mass at all, sidestepping the rocket equation's exponential fuel mass penalty entirely. This is also why, despite Project Daedalus representing a serious, technically detailed engineering study conducted by credentialed aerospace engineers, the concept was never seriously pursued beyond the paper design stage, since the practical challenges of manufacturing, launching, and assembling a 54,000-ton spacecraft in Earth orbit, let alone sourcing the specific fusion fuel isotopes it called for, remain far beyond any realistic near-term technological or economic capability. Antimatter propulsion represents another theoretically compelling but practically extraordinarily challenging alternative concept. When matter and antimatter come into contact, they annihilate each other completely, converting their entire mass directly into energy, according to Einstein's famous equation, releasing far more energy per unit of mass than any chemical or even nuclear fusion reaction could achieve. In principle, a spacecraft using antimatter-matter annihilation as its propulsion mechanism could theoretically achieve extremely high specific impulse, essentially getting far more thrust out of a given mass of propellant compared to any other known propulsion method. The problem, and it's a truly enormous one, is that antimatter is almost unimaginably difficult and expensive to produce and store using any technology available today or realistically foreseeable in the coming decades. Current particle physics facilities, like those at CERN, can produce antimatter, but only in absolutely minuscule quantities, measured in nanograms produced over the course of months or years of dedicated operation, at a cost that would translate to many trillions of dollars per gram if scaled up, making the antimatter fuel requirements for any meaningful interstellar propulsion mission, likely measured in kilograms rather than nanograms, economically and technologically inconceivable using any foreseeable production method. There's also the formidable challenge of actually storing antimatter safely, since it annihilates instantly upon contact with any normal matter, requiring sophisticated magnetic or electromagnetic containment systems that themselves consume significant power and add mass and complexity to any proposed spacecraft design. Because of these fundamental production and storage challenges, most serious researchers in this field consider antimatter propulsion to be far more speculative and further from practical realization than either nuclear pulse propulsion or laser-driven light sail concepts, despite its theoretically superior energy density, essentially placing it in a category of propulsion concepts that remain scientifically valid in principle, but functionally unrealizable given any technology we can currently imagine developing within the coming century. Generation ships represent an entirely different philosophical and engineering approach to the interstellar travel problem, one that essentially accepts the reality of multi-century travel times rather than attempting to circumvent them through exotic propulsion breakthroughs. Rather than trying to achieve extremely high velocities to minimize travel time, a generation ship concept envisions building an enormous self-sustaining spacecraft, essentially a small, enclosed artificial world capable of supporting a human population across multiple successive generations during a journey that might take several hundred or even several thousand years, with the original crew's descendants many generations removed, eventually arriving at the destination star system, having lived their entire lives, generation after generation, entirely within the confines of the ship. This approach sidesteps many of the propulsion challenges we've discussed, since it doesn't require achieving anywhere near relativistic speeds. Even the Voyager probe's roughly 17 kilometers per second, extrapolated to a multi-thousand-year journey, or a somewhat faster but still conventionally achievable velocity, would theoretically suffice for a generation ship design. Given enough patience and enough generations willing to live and die entirely within the vessel's confines, but generation ships introduce their own entirely distinct set of formidable challenges, most of which are biological, sociological, and psychological rather than purely physical or engineering-based. Maintaining a genetically healthy, sufficiently diverse human population across dozens or even hundreds of successive generations within a closed environment without the possibility of introducing new genetic diversity from outside presents serious challenges related to genetic drift, inbreeding, and long-term population health, requiring careful population genetics planning and potentially frozen genetic material banks to maintain adequate diversity across the centuries-long journey. Beyond the purely biological concerns, there are profound sociological and psychological questions about how a human society, confined entirely within an artificial, enclosed environment for generation after generation, would actually function, govern itself, and maintain psychological well-being and social cohesion across timescales far longer than any historical human society has needed to sustain itself within a single, unchanging, physically isolated environment. Historical and even contemporary examples of extended isolation, like long-duration Antarctic research stations or extended submarine deployments, offer only limited insight, since even these extreme examples typically involve isolation measured in months rather than the multi-generational timescales a genuine interstellar generation ship would require. And none of them involve people being born, raised, and living their entire lives without ever having any prospect of leaving the confined environment they were born into. An entirely different psychological and sociological situation than anything humanity has directly experienced before. Some researchers studying this question have raised the disturbing possibility that a generation ship's population over sufficiently many generations might gradually lose the technical knowledge, motivation, or even cultural memory of the original mission's purpose, potentially leading to social breakdown, the abandonment of critical maintenance responsibilities, or a complete loss of the original scientific and exploratory goals that motivated the mission in the first place, a scenario that's been explored extensively in science fiction, perhaps most famously in author Brian Aldiss's 1958 novel Non-Stop, which depicts exactly this kind of generational knowledge collapse aboard a fictional generation ship. Given all of these compounding challenges, most serious contemporary researchers and space agencies tend to view generation ships as a less immediately practical approach compared to either robotic probe missions, which avoid the entire question of human survival and psychological well-being across centuries, or more exotic but theoretically faster propulsion concepts like laser-driven light sails, which, despite their own formidable challenges, at least offer the prospect of completing a mission within a single human lifetime or generation, rather than requiring an entirely self-sustaining, multi-generational closed society successfully surviving an open-ended, centuries-long journey through the harsh vacuum of interstellar space. We've only scratched the surface. The deeper you go into space, the darker and stranger it gets. Click the video on your screen now and explore why space gets more terrifying the further you travel. You won't look at the night sky the same way again.